morning. This is again Dr. Jingbo Louise Liu from Texas A&M University, Kingsville. So today we are going to discuss your experiment number 7, solubility and the common ion effect. There are 3 objectives in this lab. First of all, you are going to determine the molar solubility of calcium hydroxide, CaOH2. Second, you are going to determine the solubility constant of this calcium hydroxide, which is a strong base. The last one, but not least, you are going to study the effect of a common ion on the molar solubility of an insoluble ionic compound. Again, this base, calcium hydroxide. Let's recall the molar solubility constant rule. So before you learned about different ionic compounds, which you dissolve them in water, there are the rules regarding the solubility. The first one is related to the soluble ionic compounds. You have 4 rules. The second part related to the insoluble ionic compounds, you have 3 different rules. So first of all, let's take a look at the soluble ionic compounds. First rule, all common compounds of your group 1A, such as lithium, sodium, potassium, and ammonia ions, they are soluble from our general chemistry learning level. Second one, all common nitrates, acetates, most of the perchlorates, chlorates, and hypochlorite, they are soluble. Most of the chlorates, bromides, iodides are soluble except when they combined with sulfur plus, Ag plus, Pb2 plus, lead, copper 1, Cu plus, mercury 1, Hg2 2 plus, they are not soluble, but most of them they are soluble, such as sodium chloride, potassium bromide, calcium chloride, they are soluble. Most of the common fluoride, they are also soluble, except they are combined with what we mentioned. If you see fluoride, chloride, bromide, iodide combined with your sulfur, lead, copper 1, mercury 1, they are insoluble compounds. Most of the common sulfate, SO4 2 negative, they are soluble, but when they combined with the group 2, such as calcium, strontium, barium, some of the transition metals, such as your silver, lead, they are not soluble. Regarding the insoluble ionic compounds, so what you can see, most of the metal hydroxide, they are not soluble, they are insoluble, except they combined with these 4 cations, lithium, sodium, potassium, and ammonium. And most of the carbonate, phosphate, they are not soluble either. Sulfate, sulfide, sulfide, they are not soluble either, unless they combined with your lithium, sodium, potassium, and ammonium. This is about the general solubility rule. And then let's take a look about the solubility and the common ion effect. If in your mixture you have cation, negative ion, those 2 ions, they can combine to form a compound. If they have very limited solubility, therefore they are going to precipitate. If you're adding the precipitating ions into your mixture, you are going to produce particles which precipitated. So you have your salt, which have a very limited solubility in water. Those salt, these compounds, you consider them insoluble or very slightly soluble ionic compounds. A saturated solution of this slightly soluble salt is a result of your dynamic equilibrium between your salt, these particles, and its ions existing in your solution. The concentrations of those remaining ions are very limited because your compound is very insoluble, slightly soluble. So again, you are going to observe a very important phenomenon you call dynamic equilibrium. Your Ksp is a dynamic equilibrium constant. And then when we discussing these solubility rules, we need to know two terms. One is called Ksp, another one called Qsp. Qsp represents the ion product expression. The Ksp is a solubility product constant. Lots of time we call it solubility product constant. For example, if we have a hypothetical compound MPXQ, this is your compound. Your MPXQ as a solid insoluble compound, you write it down as a solid. This solid is going to be ionized to P times Mn plus Q times Xg plus. And then your equilibrium constant, if it's at equilibrium, otherwise if it's at any time, your ion product expression equals to the m to the power of m to the power p x anion negatively charged ion to the power q. So if this product at equilibrium is called solubility product constant. Slightly soluble or insoluble compounds, ionic compounds, we call them salt, have a very limited solubility, meaning this concentration will be very low. And the Ksp for a slightly soluble or insoluble compound will be a very small number. The molar solubility refers to the number of moles of your salt, of your compound, dissolves in the aqueous solution per liter. So to repeat, molar solubility is the number of moles of your compound that dissolves per liter in your aqueous solution. Let's take a couple examples. How we are going to write it down your Ksp or Qsp. Lots of time we are going to use Ksp because you have the meaning. So I have three examples. I have magnesium carbonate, iron 2 hydroxide, and calcium phosphate. Three different reactions. How you are going to write it down the balanced equation is critical. And then from the balanced equation, you are going to ignore the solid. You simply consider the 2 or 3 different types of ions which are in equilibrium in your solution. So let's try the first one, magnesium carbonate. Again, it's a solid, so it's an insoluble compound. You write it down as a solid. It's going to break down to magnesium 2 plus and carbonate. Your Ksp equals Mg2 plus concentration multiplied by carbonate concentration. Similarly, you have second one, iron 2 hydroxide, FeOH2. Solid is going to break down to 1 moles of your iron 2 plus and 2 moles of your hydroxide. And then your Ksp written down as Fe2 plus times hydroxide to the power 2. The last one, calcium phosphate, which is solid, going to be dissociated into 3 moles of calcium 2 plus and 2 moles of your phosphate. Ksp will be written down as calcium 2 plus to the power 3, phosphate 3 negative to the power 2. That's how you write it down your Ksp expression. If you have this Ksp expression, you can determine Ksp if you know solubility. Otherwise, if you know solubility, you can determine Ksp. You also can determine common ion effect, which result in the decrease in your solubility. Let's take a look at the first example. You have the lead 2 plus, lead sulfate, which is a very important component in your lead acid battery, which you used in the car. The solubility of this lead 2 sulfate is very limited at 25 degree in water, so which is found to be 4.25 times 10 to negative 3 grams per 100 milliliters. What's the KSP value of this lead sulfate? First of all, you are going to write it down a balanced dissolution equation. Second one, you are going to find the moles of the dissociated ions. In other words, you want to find the molar solubility. And then you are going to convert the solubility from any unit into the moles per liter. And then you are going to substitute the known values into your KSP expression, solubility product constant expression. So let's construct a balanced reaction. Lead 2-phosphate solid is going to break down to lead 2+ in aqueous and sulfate in aqueous. This equation is going to have a KSP expression as lead 2+ multiplied by sulfate negative ion. So you are going to convert this solubility into molar solubility. So you have 4.25 times 10 to negative 3 grams per 100 milliliter solution. You want to convert this 100 milliliter into liters. 1 liter equals 1000 milliliter. You are going to convert these grams to moles. 1 mole of your lead sulfate equals 303.3 grams. This is your molar mass. My calculation is 1.4 times 10 to negative 4 moles per liter. And then your KSP equals your lead concentration multiplied by sulfate. 1 mole of this lead sulfate produces 1 mole of lead 2+ and 1 mole sulfate, meaning your molar solubility of your lead and sulfate both the same as 1.4 times 10 to negative 4. So therefore you calculate your KSP. My determination is 1.96 times 10 to negative 8. This KSP is an equilibrium constant, has no unit, is a unitless or dimensionless value. And then let's try another one. If you know the KSP, how do we determine the molar solubility? For example, your calcium hydroxide, which is named as slaked lime. This slaked lime is a major component in your mortar, plaster, cement. This solution of calcium hydroxide are used in industry as a very cost-effective and strong base. So what I want our students to do is to determine the molar solubility of your calcium hydroxide. If you know KSP, which is determined to be 6.5 times 10 to negative 6, you are going to again to construct your SCE table, and then you are going to write it out the dissociation, dissolution, ionization equation, and your KSP expression. From the KSP, you determine the molar solubility S. Usually use a capital S to represent a molar solubility. So let's construct your balanced reaction. Calcium hydroxide, CaOH, which is a solid, produce calcium aqueous and produce 2 moles of hydroxide. And then this is your balanced reaction. Your initially you have 0 hydroxide, 0 calcium. If you have a solid, you simply ignore the solid. The change in concentration, you assume is S for product. If you have calcium is 1 moles plus S. If your hydroxide 2 moles will be plus 2S. At equilibrium, you have the S, you have 2S for hydroxide. And then you are going to set it up your balance, you set it up your KSP. KSP equals to the S calcium to the hydroxide to the 2 power 2. Hydroxide concentration is 2S. Therefore, you solve for your S, which equals to the root cubed of your solubility KSP divided by 4. My calculation is 1.2 times 10 to negative 2 moles per liter. Molar solubility of your calcium hydroxide is 1.2 times 10 to negative power 2. So what is the common ion effect? common ion effect, it refers to the effect you are going to result in the equilibrium shift to the left for this, for example, lead chromate. If you have your lead chromate, which is solid, which is not solubility, this compound, more or less a very small portion, is going to be break down to lead 2+ and chromate aqueous solution. So in this case, you have this balanced equation. Into this solution, you're adding, say, chromate. Adding chromate, what's going to happen? Based on your Ricard principle, if you add an ion, which is common to the salt, your equilibrium is going to shift it to the left to compensate these added ions. So again, your equilibrium is going to go to the left to favor more solid formation. This effect you call the common ion effect. Common ion effect is resulting from the addition of the ions to the existing equilibrium. This common ion effect usually resulted in the decrease in your molar solubility. For example, still we are using the above calcium hydroxide solution. You are going to add 0.10 moles per liter of your calcium nitrate into the calcium hydroxide saturated solution. What is the new solubility? Again, you are going to construct the res table and then the expression of your KSP, and then you calculate your new molar solubility. So let's see your initial change and equilibrium. Initially, you add 0.10 moles, and hydroxide you can say 10 to power -7. This value is very small. You again ignore it. Change will be S for calcium, will be 2S for hydroxide, both positive. And the equilibrium concentration for your calcium will be 0.1 plus S, for your hydroxide will be 2S. And then in this case, your KSP is written down as 0.1 plus S times 2S. 0 plus 1, 0.1 plus S, this is approximately equals 0.1. The reason is S, you will find, is much smaller than 0.10. So you calculate your S again, you calculate it. My calculation is 4.0 times 10 to -3, meaning you are going to double check your approximation. So you are going to use this calculated solubility S divided by your 0.1. If this number is applicable for that 5% rule, if 5% rule is followed, your approximation is justified. My calculation is 4%. In that case, meaning your approximation is justified. Otherwise, you have to carry on this value of your S. And the last 2 points is about the experimental procedure. You have 2 major procedures. You are going to prepare your stock solution of calcium hydroxide. Actually, you are going to produce a saturated solution, and then you are going to titrate this calcium hydroxide using a standard acid solution, hydrochloric acid, and then you calculate your hydroxide and then KSP. The last point will be your common ion effect. If you're adding calcium chloride into the solution, so I want you to determine the new molar solubility. You essentially follow the same rule to determine it. And also I give everybody one more different titration curve. One of the titration curve is discussing about using strong acid to titrate the strong base. You see your base has a very high pH value. With the addition of your acid, you are going to see a dramatic pH change. This is called strong acid, strong base, strong acid titration. If you have a weak base, strong acid titration, you are going to see a buffer region. In your case, you are not going to observe buffer region because your calcium hydroxide is a strong base. At equivalence point, you are going to see your indicator, in this case is your methyl orange, is going to change from yellow to very fainted red. And then you may add in half drop of your hydrochloric acid to maintain the persistence of your endpoint, and then recording your hydrochloric acid, so you are going to do the determination of the different concentrations. This slide also gives you some ideas about the different indicator where the pH, where the color changes may happen. At this point, I'm going to conclude today's discussion. So have a nice day. Thank you so much.